Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means. In this video, we're going to focus on topic 7.5, carrying out a test for a population mean. So remember, a test for a population mean consists of 4 big steps. And in this video, we're going to cover steps 3 and 4. Remember, in topic 7.4, we looked at steps 1 and 2. All right, so let's briefly remind you of the steps 1 and 2. So when you're conducting a one-sample t-test for a population mean, step 1 is really just identifying the parameter of interest. What is the problem dealing with? Like, am I dealing with the mean weight of alligators, or am I dealing with the mean height of teenagers? What are you talking about? And then you want to name the test. It's called a one-sample t-test for a population mean. And then, of course, we have to write the null and the alternative hypotheses based on the problem that we were given. Now, step 2 is to really build that sampling distribution. So you got to check the conditions as you're building it. You got to make sure that you find the mean, the standard error, and the shape, which is of course going to be a t-distribution for the sampling distribution. Once all that's ready to go, it's time to move on to step 3. In step 3 is where we turn our attention to our sample. So what we want to figure out is, where is our sample mean? And what I mean by that is we have to see where our sample mean provides significant evidence that we could show that our claim is correct. So remember, the whole goal is that we think the alternative is true, and that's what we would like to show. So the only way we could show that the alternative hypothesis is true is if we have good, solid, significant evidence. So what we need to do is see where our sample mean fits in to that sampling distribution that we built. Now, making a picture of that sampling distribution is not a requirement, but it really does kind of help seeing where your sample mean falls in. And then you could literally see, is it significantly high, significantly low, or no, pretty standard in the middle. So the position of our sample mean in that sampling distribution is called a test statistic, otherwise known as a t-score. Now, it's not a z-score, remember, because, well, it's a t-distribution. It's a t-score. But the idea of how to solve it is exactly the same. So to find our t-score, we're going to take our sample mean x bar. We're going to subtract the mean from the null hypothesis. That's why it says mu sub 0. That's the mean that we assume to be true in the null. And then we're going to divide by the standard error, which this right here is the formula for standard error. And remember, because we are using S in place of sigma is exactly why we have to use the t-distribution. Now, if you accurately drew the picture of the sampling distribution, you should be able to literally see where your sample mean fits in, but the t-score is something that you need because it tells you exactly how many standard errors your sample mean falls above or below the mean. So the next question really becomes, how likely is our sample? Now that we've located our sample mean in the sampling distribution, we need to ask ourselves, how likely of a sample is it? Of course, that's the p-value. So remember, the definition of a p-value is so vital to your understanding. A p-value is the probability that any other sample mean is more extreme than the one we found on the assumption that the null hypothesis is true. So again, really make sure you understand that. It's the probability number. First, I guess, you need to understand sampling distribution shows millions of sample means, not just ours. So the p-value is the probability that any other sample mean comes back more extreme than the one we found. Now, what do we mean by more extreme? Well, that's the direction of your alternative. If we think that the alternative is that it's higher, then more extreme means higher. If our alternative is lower, then or more extreme means lower. But perhaps the one thing that a lot of kids forget about a p-value is that it's on the assumption that the null hypothesis is true. Remember, we built that sampling distribution on the idea that the null hypothesis, the mean from the null hypothesis, is smack dab in the middle as the true value. So how do you find a p-value? Well, we can't use normal CDF. Remember, we're not using a normal model here. We're using a t model or a t distribution. So we're going to use TCDF. Now, you might not have even realized this, but this is on your calculator. So when you go to second vars, you will notice just a couple clicks down, number 6 here, TCDF. So we'll never use TPDF, kind of like we never use normal PDF. So again, TCDF will look either above a t-score, below a t-score, or in between two t-scores. So to officially find a p-value, it is the probability that a sample mean is greater than ours or less than. Again, it's all depending on your alternative. I just choose the generic greater than. To find that, we're looking equally at the probability that a t-score is greater than our t-score. And to do this, we are going to utilize TCDF. Now, TCDF is going to need our t-score. Then we're going to go all the way towards infinity, which on our calculator we're going to use is 99. And then we need a mean of 1. Mean of 0, standard deviation of 1, and then the last thing you're going to be asked for is the degrees of freedom. And then when I show you this on the calculator here in a moment, you'll see this. And remember, the reason why you need the degrees of freedom, which is simply sample size minus 1, is because there are many different t-models out there, not just the standard one. So let's actually look at two examples. So here are two different t-distributions with sample size of 35, which is 34 degrees of freedom. So on the left here, I have a t-score of negative 2.1. So that's the t-score based on our mean. So that's where our mean fell. Our mean fell 2.1 standard errors below the truth in the center. Now, the p-value would be the probability that a sample is less than that. I'm already on the low side, so or more extreme would be even lower. So I'm looking at the probability that a t-score is less than negative 2.1. And to do that, I'm going to grab my calculator. I'm going to grab the TCDF. So I want to look less than, so lower is going to be negative 99. The upper value, because I'm trying to find that gray region, that's my p-value down there, is negative 2.1. And then you'll notice I now need the degrees of freedom. The degrees of freedom for this particular model, like I mentioned, came from a sample size of 35, so it's 34 degrees of freedom. And we get 0.0216. So that would be my p-value, 0.0216. All right, let's look at this example over here on the right-hand side. All right, here we have a t-score of 1.23. So you could clearly tell that's not really that high. So obviously that came from a mean. Again, you can't get a t-score unless you calculate it based on the formula I showed you earlier. And then what you're going to do is you're going to find the p-value. Again, the p-value is the probability that a sample mean is more extreme than ours, which would be anything above ours because we're already on the positive side. So right here, we're going to look at the probability that a t-score is greater than 1.23. So to do that, I'm going to go and grab TCDF again. Now this time I'm going above, so I'm going to start with 1.23. I'm going to go to 99, that's acting as my infinity. And once again, 34 degrees of freedom for this particular problem. And I get 0.1135. And if I actually, for a second, put my calculator in the middle of the screen here, you could see that on the right-hand side here with a t-score of 1.23, which is not that high, there is a large probability above it. In this case, about 11% probability, so big chunk there. On the left-hand side here, negative 2.1 is a fairly low t-score. It's getting there. It's kind of low. And obviously that produces a pretty small p-value because there's very little samples, about 2% below that. So that is how you get p-values when you work with a t-distribution. So let's quickly recap step 3. Step 3 is, again, a lot of kids' favorite step. It's quite easy. You're going to find the test statistics, the t-score of the sample mean described in the problem, and then you're going to find the p-value of that sample mean. So you got to find the t-score first. The reason for that is when you go to use TCF on your calculator, it only uses t-scores. So please make sure you're showing all of your work nice and neat for how to find that t-score and that you're properly labeling your p-value. All right, let's move on to step 4, which is making our final conclusion. In step 4, we're going to make that conclusion, but it all starts with figuring out if you truly are significant. So is my sample significant? And we're going to need the p-value to help us understand that. And we need to compare that p-value to what we call the significance level, or alpha. Alpha and the significance level are the same thing. The two most common significance levels are 1% and 5%, 0.01 and 0.05. And essentially what we're doing is we're drawing a line in the sand saying anything less than alpha is considered significant. So if we do draw the line in the sand at 1%, any p-value below 1% would be significant. That's a significant sample showing that we do have strong evidence, otherwise not significant. So this creates two different conclusions. If the p-value is less than the significance level, then the sample mean found in the problem is significant. We're going to reject the null. We do have the evidence that the alternative is true. If the p-value is not more than the significance level, that the sample mean found in the problem is not significant. Fail to reject the null. So if we go back and look at our two examples, the one on the left, let's just say we're going to use the 5% level here. On the left, the p-value is about 0.02. So since 0.02 is less than 5%, that would be significant. That's a significant sample. In that case, we'd reject the null. On the right-hand side there, our p-value was 0.11 approximately, and that's greater than our alpha level of 0.05. So in that case, we would not reject the null. We would fail to reject the null. We do not have evidence to go with the alternative. And this should actually make sense, because when something super low happens, or super high, this means that the middle's wrong, because we don't expect things that low to happen. And that's why we're going to reject the middle. We're going to reject the null that we put in the middle. But when something very likely happens, meaning that it's actually pretty close to the middle, well, that doesn't necessarily mean the middle's wrong. It just means that we're seeing some slight variation that's just due to sampling. So that is how we make our decision. Pretty straightforward, pretty simple, but you do need your alpha value. Now, if a problem does not give you an alpha value, you actually get to pick whatever one you use, but 1 and 5% are the most common. We do have to make sure that we properly word our conclusion. So when we do have significant evidence to reject the null and say that we do have evidence that the alternative hypothesis is correct. When a sample mean is very significant, high or low, right on the ends, on the far left, far right, that will create a very low p-value. This is telling you that the probability of the sample mean found in the problem, or more extreme, is very unlikely, assuming the null is true. The idea is that if the sample mean found in the problem was so unlikely, but it did occur, again, the only conclusion that we can make is that the null must be wrong and the alternative is true. If a sample mean is found to be significantly higher or lower than the null, the only explanation is that the null is wrong and the alternative is true. And the reason is that we just don't believe in those significant things happening. So the only explanation for why something so significant is happening is that this value we put in the center, the null hypothesis, is wrong. Now, what about when we don't have enough evidence? Well, when the sample mean found in the problem is not significant, meaning it is not unusually high or low on the assumption that the null is true, then we fail to reject the null. This means there is not significant evidence that the alternative is true. Here, if a sample mean is just a little higher or a little lower than the null hypothesis, which is actually going to produce a large p-value, because a p-value is going towards the tail, so if your sample is close to the center, then you're going to have a big p-value to the right. Well, the explanation is probably just sampling variability. It doesn't necessarily mean that the null is false. Go back to my picture here that's, I know, getting a little bit messy, but the idea here is on the right-hand side here, the t-score was 1.23, which really isn't that unusually high. And notice all the area more extreme than that. And it actually was pretty big, about 11%. And again, what could be the explanation for this? Well, nothing. Sampling variability. Samples sometimes are a little high or a little low. It doesn't mean anything. But on the left-hand side, when a sample is really, really low or really, really high, that's what does tell you something. So please make sure that we never ever accept the null. don't ever say that. We just say that we do not have enough evidence to take on the alternative. Because at the end of the day, we still don't know if we're right or wrong, but our evidence just doesn't give us what we need to go with the alternative. Here's a nice summary of all this. So it really does take a couple things. First, we got to find the t-score. Here is the formula for a t-score. Pretty simple. Then you got to find the p-value using the t-CDF. Then we have to compare that p-value to our alpha level. Remember, the alpha level is the significance level. It's the exact same thing. Alpha level, significance level mean the same thing. And if you have a small p-value, then that's when you reject a null. If you have a large p-value, you fail to reject a null. All we have to be able to do is put that into nice words that have context to our problem. So let's start with looking at our two examples that we've been working with, caffeine and thermometers. All right, so the first example that we're going to take a look at here was our caffeine example. Let's refresh your memories what it was. The makers of a popular caffeine pill want to make sure that their tablets don't contain too little caffeine. So they inspect a random sample of 35 tablets from the production batch and measure the caffeine in each of those pills. When the production is working properly, there should be a mean of 220 milligrams of caffeine. So the mean and standard deviation of the sample was 218 milligrams and 3.2 milligrams. Is this significant evidence that the pills contain a mean less than 220 milligrams? Let's briefly run through steps 1 and step 2. This is a one sample t-test for the population mean amount of caffeine of tablets produced by the company. The mu equaling 220 is the null. We're saying that, hey, we got to believe that that is still true, but the alternative is our belief that it's less than that. Step 2 is building the sampling distribution. Got to check all those conditions as always. The center, the mean of our sampling distribution is going to be 220. That's the null. The standard error, which is taking 3.2, the standard deviation of our sample, divided by our sample, the square root of our sample size, is 0.541. Remember, you don't have to draw this picture, but it is really nice when you're trying to actually see where your sample fits in. All right, now step 3, my favorite part. All right, the t-score is taking our sample mean, 218, minus the mean from the null, 220, divided by that standard error of 0.541. Now that gives me a t-score of negative 3.697. Now if I have my picture drawn, which is not a requirement, but if you have the picture drawn, you could literally see how unbelievably low this is. A t-score of negative 3.697 is literally off the chart, and you could actually see that a sample of 218 on average would be really, really low. I mean, it's literally off the chart. 218 is below that 218.377 mark. So now to find the p-value, and please make sure you have all of this, on your paper. This is exactly how it should look on your paper, on your work, is we're trying to find the probability that a sample mean, any other sample mean, x bar, is, it should be a less than sign, right? We always make mistakes. There it is. Less than 218, because I'm already low. My alternative is that I think it's low, or more extreme would be even lower. So I'm going to look at a t-score that is less than negative 3.697, because that's the t-score. And to get that p-value, I'm going to use t-CDF on the calculator. And when I use t-CDF, I'll actually just show you here me doing it. It's really simple. Just going to go to second vars here, t-CDF. I want to look below, so I'm going to start off with negative 99. And I'm going to go up to that z-score of negative 3.697. And don't forget your degrees of freedom. We had 35 in our sample, so that's 34 degrees of freedom. And that's how I got the 0.000382. All right, so let's refresh your memories in terms of what that p-value tells you. It means that there's a probability of 0.000382. The sample mean of 35 tablets has a mean of 218 or lower, assuming that the null of 220 is true. All right, this is certainly a significant sample. So now all we have to do in step 4 is compare our p-value to our significance level. Again, if you go back and look at the problem, it never gave you a significance level, so I'm going to go with a pretty standard 0.01. And obviously, I'm less than 0.01, so I'm going to reject the null. Rejecting the null means that there is significant evidence that the mean amount of caffeine in the tablets is less than 220 milligrams. Now, a lot of kids are probably going to stop there, but I'm going to keep going because I want to give some meaning to this problem. What does it mean for the production if I have just proven that the tablets are less than 220? Well, I would hope that production of the pills should be stopped and that the production should be fixed so that the mean can be back up to 220. Because if I work for this company and I just found out, oh my gosh, the mean in these pills is not 220, it's less than 220, well then I should probably do something about it. And that's why I added that extra sentence there. So, when you actually sit back and look at this problem and follow the steps, I don't know, I think it's very interesting. I think it's a cool process. I think it should make a lot of sense to you. And individually, each step's pretty easy. All right, let's take a look at our thermometer example here. If you remember, what we were doing is we were trying to determine if there was a significant difference between the readings of two different thermometers, A and B. And we did a matched pair example here where we had 11 subjects and we simply measured them twice, once with temperature A and once with temperature B. So I know that this looks like I have two sets of data, but remember, I only have one sample. All I care about is the difference. So if you go back to topic 7.4, we talked a lot about this. I want to go over all that. But essentially, I don't care about any of the numbers on the screen right now. All I cared about were the differences. So I actually made a list of all of my differences between the two readings, and I found a mean of those differences, 0.0545, and the standard deviation of those differences. So my name is a one sample t-test for the mean difference between the two brands of thermometers. I'm going to go with the null that there is no difference. I'm going to go ahead and say that these two thermometers are one and the same. Doesn't really matter. And the alternative is that, hey, I want to show you that there is a difference. I'm trying to show that there is certainly a difference. I never said one was better than the other, one was higher than the other. I'm just looking for a difference, not equal to 0. All right, so step 2 was building that sampling distribution based on the null being true. So that's why I put 0 in the middle. I assume that the mean of all possible sample differences was 0. And the standard error is taking my standard deviation, 0.333, divided by the square root of the sample size, which is exactly why I have to use a t-model with 10 degrees of freedom. 11 minus 1 is 10 degrees of freedom. So there it is. Now, step 3. So my t-score based on my sample. So my mean was 0.0545 minus 0. And I'm going to divide, because 0 was the center, the mean, right? What I'm assuming to be true at least. And then I'm dividing that by my standard error, 0.10 or 100, and I get 0.545. So that is not a very high t-score at all. You could literally see it. It's not that high. It's not even 1 standard deviation above. And the mean of 0.0545 also falls right where I kind of put that mark, 0.0545. If this is 0.1 and this is 0, then obviously 0.0545 is going to be somewhere pretty close to in between there. And that's actually going to produce a very large p-value because there's lots and lots of samples that are going to be more than that because it's, again, not that high. So I don't think this is significant at all. Though when you find the p-value, since it's already a positive t-score, we are going to look more, so that would be even higher. So we're going to look at the probability that a sample mean comes back more than mine, which is a t-score, I'm sorry, another typo there, a t-score that's more than 0.545. That was my t-score. And I'm going to use TCDF. I'm going to look above my value. I'm going to go to 99, but that's infinity, right? And don't forget 10 degrees of freedom. And I am going to double that. Make sure I double that. If you don't double it, it's like 0.29, something like that. So if you don't double it, it's about 0.29. But I do have to double it. The reason why I have to double it is because my alternative was not equal to, which means that if I would have been on this side, then I would have equally been showing that this is not significant. The idea is that when it's not equal to, it's two-sided, meaning either side of the model is where you're looking for. Well, you can only look at one side ever at a time. You can only do one thing at a time. So, but I have to assume that the other side would be exactly equal because of symmetry. So that's why we just double the p-value, and that's how I got 0.5977. Now, I don't really think it matters what significance level you choose. That is very high. but I went ahead with 0.05, and since my p-value is way greater than 0.05, I will fail to reject the null hypothesis. There is no significant evidence that there is a mean difference between the two thermometers. Yes, some patients might have a slight difference in their readings, but that is on a single patient basis. But what we're saying here is that there's no significant evidence that on average there is a difference between these two thermometers. Sometimes there could be negative differences, sometimes there could be positive differences. So that's why I'm saying, listen, at the end of the day, I don't think there's any true mean difference between the two thermometers. The two thermometers are essentially no different than each other on the average when giving temperature readings. And, it's important for you guys to understand, if you go back and look at the data, there were lots of people where there was a slight difference. But again, that's an individual basis. What I'm trying to say here is that there's no evidence that the mean of all differences is anything that matters. It's just not significant. So, pretty easy problem. Hope you understand the conclusion. Based on all the different pieces and parts that are working here. All right, the only thing we have left to talk about are possible errors. I don't want you to forget about the existence of type 1 and type 2 error. So we've already discussed this in Unit 6. Let's talk about it one more time again. A type 1 error is in actuality the null hypothesis is true, but the error that is made is that the null is rejected and the alternative is taken as the truth when it is not. So the alternative is not true, but the error is we think it is. Remember, the null is really what's true. A type 2 error, in actuality, the alternative hypothesis is true, but the error that is made is that the null is failed to be rejected and a null that is false is kept. Another way of viewing this is with the tree diagram. I think it kind of, for some students, makes a lot of sense. So what's true? Either the null is true or the alternative is true. So the first idea is that the null hypothesis is really true. The alternative is wrong. So if this is what's really true, one thing that we could do is we fail to reject the null. This is the right decision. This is doing the right thing. The null is true. We should fail to reject it. But a type 1 error is when we do reject that null and we believe the alternative is true, but it's not. The probability of this happening in any given problem is equal to your alpha level. So your significance level is actually equal to the probability of a type 1 error. So if doing the wrong thing is your alpha level, then 1 minus alpha would be the probability that you fail to reject the null when you should, because remember, the null is really true. Now the other opposite end of this is that the null hypothesis is really false and the alternative is true. Again, the alternative is true. Well, if we reject the null, that's the right decision. If the null is wrong, the null is false, the alternative is true, then you should reject the null. That is making the right decision. Now, the probability of doing this actually has a name. We actually call this power. Now, the type 2 error is when, again, remember, the alternative is true, but we fail to reject the null. We keep a false null. This is a type 2 error, which is 1 minus power. Now, don't ever worry about actually calculating for this course what the probability of power is. Just understand the name of it. So let's talk a little bit more about power, but let's do so with an example. So let's actually use our caffeine example here. So here's the null and the alternative hypotheses. Now, when I'm talking about type 1 and type 2 error, don't reference your problem. Remember, your problem was your problem. You made the best decision you could. Type 1 and type 2 error are more conceptual things we just want you to understand. So I actually number the null as 1 and the alternative is 2. Numerical order 1, 2. This actually helps me. So a type 1 error is when the null is true. The average amount of caffeine in the tablets really is 220 milligrams, but the error is I think it's less. So this is basically my machines are working fine. Production is working great. It's really true that it's 220, but I stop production. I try to fix a problem that doesn't exist. That's obviously an error. A type 2 error, again, that's why I numbered the alternative number 2. A type 2 error is the alternative is true. There really is less than 220 milligrams in each pill, but the error is I fail to see that. I don't conclude that. I fail to reject the null. I keep a false null. This is a bigger problem if you ask me, because I'm now going to continue production. I'm going to sell these pills that in actuality are less than 220 milligrams on average of caffeine content. So I'm actually lying to my customers. So in type 1 error, I'm trying to fix a problem that doesn't exist. Obviously, that's a problem, but hey, at least I'm not lying to my customers. a type 2 error is that there really is a problem. It really is less than 220, but I don't see that. So make sure that in any given problem you can describe those things. Now let's talk about power a little bit more here. Obviously, power is doing the right thing, right? If the alternative is true, you should reject the null and go with that alternative. Doing that is power. So the big question is, how do we get more power? 3 ways, but only 2 of them I like. Increase your sample size. Bigger samples are always going to be closer to the truth. And if the truth is far away from the null, then a bigger sample will help me see that. Increase the significance level. If I make my alpha higher, then the probability of type 2 error actually goes down. So with a higher alpha, you will be more likely to reject the null. If I'm more likely to reject the null, then I'm going to reject the null more often. But I actually don't like doing that because we don't want higher alpha, because now we have an increased risk of type 1 error. So the third option is to gather evidence that's actually further from the null, right? So when the actual truth is very far from the null, then your sample statistics should show that, and that's going to give you more power. So let me give you an example. If the truth was actually 190 milligrams, if that was really the truth, that is way far away from the null. So if that's the truth, then samples should show me that, because that's what samples do. They reflect the truth. And then I'm going to be like, oh my gosh, wow, well, this is really less than the null. I'm going to reject it. So bigger sample sizes will give us more power. And if the truth is really far from the null, well, then we should see that and hence reject it and go with the alternative. And again, just to kind of give you a counterexample here, if the truth was 219, well, okay, 219 is only a little bit less than the null. So if I collect samples, they might be right around 219. Now, technically that is less than 220, but it's so close, excuse me, that my samples might not show me that, and then I might not necessarily reject the null. So the further the truth is from the null, the more likely you are to see that and reject it. So hopefully that makes sense. All right, guys, that's it. I am going to make another video here for some more examples of running through all 4 steps. If you would like to watch it, definitely can help. The more examples you see, the better. All right, that's it for 7.5.